let's continue to the presentation. Our next speaker is, please, Professor Kami, are you introducing?
I'd like to thank Dr. Duncan for a very interesting talk. And we move on to Professor Lake's presentation. So Dr. Larry Lake is a Shahid and Sharon Ullah Chair Professor in Hildebrand Department of Petroleum and Geosystem Engineering at the University of Texas at Austin. He's a well-known researcher in the area of enhanced oil recovery, reservoir engineering, reservoir characterization, reservoir simulation, CO2 sequestration, and geochemistry. He served as the PI for the Center for Frontiers of Subsurface Energy Security, CFES, at UT Austin. Also, he has served as the chair of the department for many, many times. So I would like to ask Dr. Lake to present his talk. I think you're muted.
And I hope that's me.
Yes.
Okay, can you see it?
Yes, sir.
Okay, good. I'll put it over here. I want to thank everybody for coming. The turnout is just super. So I'm very pleased with this. And I'll be happy to answer questions either by text or by email after the presentation is over. I'm very pleased with the title. It says from EOR to CCS, and it says the maturation and migration of a technology. And it is true, we have a technology that has matured and is on the very cusp of migration to a different technology. Most of my talk will be about CO2 EOR, and I've taken a lot of information from other sources, which I probably will not have time to credit individually, but there are the names of folks. And here is a cartoon, one of many, that shows CO2 EOR, which consists of injected CO2 here. And as Dr. Duncan pointed out, most of the CO2 in the United States is coming from natural sources, which is here. It goes into the ground. It produces oil over here, and a great deal of it, something like half of the CO2 produced over here is recycled. So that after a while, the purchased CO2 here, it goes down with time. But at the same time, the CO2 is dissolved in the reservoir. And so this presentation is talking a little bit about both the oil recovery and the storage aspects here. And I always show this slide because, well, I don't know much about the field of anything. And so I wanted to show it up here for you. Those of you that's been in the field a lot, it might make you feel a little more comfortable. Now, from here on, the presentation is based upon a paper that was written by myself, Mohammed Latfalahi, and Steve Bryant. It's 2018. It's in a publication which may not be easy to get to, and I'm sure that Dr. Sepineri will be happy to send you a copy of this should you like it. And it's titled 15 Years of Field Observations and Lessons of CO2 Storage for CO2 Enhanced Oil Recovery. And I forgot to say on a previous slide that that's what the U in CCUS is CC, carbon capture, utilization, and storage. Before that, it was just CCS. So there's the paper. And just something here. First of all, 50 years of experience with wells. We've learned that operating wells, injectors, and extractors, it's been operated for decades, is practical. We've learned that fluid production EOR guarantees pressure maintenance or management, and that may not be true in carbon capture alone. More about that later. And we've learned that the injectors do have to have special treatment, adds to the cost of them. And I don't know much about this, but I'll basically show a slide that somebody gave me to see what sort of treatment requirements on the method of construction on the right-hand side for each wells to prevent the different things. The history is, and I took this out of the presentation, is that injectivity of a well typically declines with time. It declines during CO2 injection. It declines during water injection, and so things usually lose injectivity, and the wells do have to be treated periodically if you can't live with the injectivity. Okay, but now on to oil recovery. So this is my favorite field case. It's a pilot scale flood, and I think this is in the Slaughter Estate unit. And I'll point out some features of this, but one of the reasons I like this is because this actually shows CO2 production here as well as oil production. And this is over here in meters cubed per day. So the first point is CO2 injection began in 1977. This was not the earliest CO2 flood. I think the earliest CO2 flood was about 10 years older. And so it is not in experimental stages anymore. This is a mature technology. And for CCS, the things that are in red are conclusions that Steve Bryant added. The CCUS should know that there's a great deal of experience in operating large-scale injection facilities. Please don't send a proposal into the Department of Energy saying you're going to study large-scale injection. That has been studied for a long time. The second thing is that this project demonstrated the feasibility of beginning CO2 after a water flood. And in fact, what actually happened here is this was pilot, and a water flood started right here in early 1973. It shows oil rate rising quickly and the declining gradually. And then it shows the gas oil ratio collapsing. And this is a fairly typical water flood response, but I will have to say that fears that you could not recover CO2 after a water flood were pretty much alloyed with this. So you can in fact do that. Second was, well, I said this before, the rapid rise and fall of the oil rate and the collapse of the GOR is typical water flood performance. The next one is the incremental oil at the time, which is here, right there in blue. Some turned out at the time of this slide, and I admit that it's a pretty old slide, but I use it even so because it makes the point that this is a mature technology. The time of the slide, the incremental oil recovery was 75% of the original in place. And you'll see in this and in previous slides, in subsequent slides, that it basically says that you can recover oil, and even if the water saturation is high. But to me, the most surprising thing, well, come on now, is the gas oil ratio, which is in yellow right here, begins to rise at the beginning, almost at the onset of CO2 injection. The gas oil ratio rises right there. And yes, some of that gas is undoubtedly a solution gas, but it definitely mostly, particularly in the later stages, is produced CO2. And in fact, you can see the gas oil ratio over here beginning to oscillate, and those oscillations corresponding to the switching between carbon dioxide and water cycles. This is a so-called WAG flood. It is surprising to me, and it's pretty common, that virtually all of the oil is produced with the CO2. So laboratory experiments and one-dimensional simulations will say that these things will form an oil bank and you will have produced a clean oil bank, but that just doesn't happen. The oil is produced with the CO2, so you should expect to separate it. Now, switching over to an equally old field, almost as old, this is Shell's flood, where flooding started in 1965. And this is the Wasson unit. This is field-scale performance. And you can tell that this is field-scale because the numbers over here are much larger. This is 100,000 barrels per day. And here's the oil response. What is curious about this, of course, is once again the CO2, the oil response started almost with the onset of CO2, but there was no bank. In the previous case, you show an increase in oil rate here, and then it came back down. That is called a bank. But in this case, there wasn't really a bank. There was just simply an arresting of the oil rate decline. So those are sort of basics. And of course, these are just two field cases. So I'm indebted to Mike Stell at Ryder Scott for directing me to this information. These are a bunch of floods that shows the incremental recovery factor versus injected CO2. And we'll show you this slide in several versions as we go on. I do not intend for you to read the field names in the caption here. Suffice it to say that it is a mixture of pilots and field cases. Suffice it to say there are some oddballs here, like this one right here, this orange one here, but doesn't seem to be leveling off. But the vast majority of them show an increase and a gradually leveling off right over here. And you see basically substantial variability in performance. It's not all Permian Basin, dominated by Permian Basin, but not all Permian Basin. They're all in the US, as far as I know. But even given that, there still is a lot of variability. Once again, the oil response was very quick. We start seeing the oil rate beginning to increase somewhere around 5% of a pore volume. Once again, the manifestation of mature technology is here. But several of these cases have injected more than a pore volume of CO2, and the ultimate recovery is 7 to 25%. Now, once I got the data, I would like to analyze it. And so one of the ways to analyze it, of course, we cannot run a numerical simulation of every single case, but is to come up with something called a simple model. And on the upper left-hand side, you see a cartoon of a reservoir that consists of a yellow and blue areas. The yellow area is swept. The blue areas are unswept. And it doesn't really matter what the cause of it is. It could be layering, it could be gravity, it could be heterogeneity, as the slide here indicates. And on the upper right-hand corner is a plot of aerial sweep efficiency. See, this is from a laboratory experiment that shows curves which look like that. And down here is an equation that has been used to fit the response of those curves. This is the incremental oil produced. This is the pore volume. This is the change in saturation between swept and unswept. And this is the volumetric sweep. And the volumetric sweep is something which I've been interested in a long time. And nobody that's ever heard me speak knows that I wouldn't talk about this at one time or another. There's a simple relationship between dimensionless time and the volumetric sweep and something called a Koval factor, which is the measure of heterogeneity of the field. A little side track here. The Koval factor was actually invented in 1963 by this guy here, and our students over the last few years have been taking this idea and basically applying it to nearly 100 field cases, and to my surprise, it works pretty well. And it's also very simple, because here is the volumetric sweep efficiency calculated from this simple equation. A Koval factor of 1 means that the field is heterogeneous. The larger the whole Koval factor is, the poorer the sweep and the more heterogeneous things are. And Mohammed can take that equation and he can fit it to the data. You see on the left-hand side is the fit of oil recovery versus dimensionless time put in. I think you have to agree that that's a pretty good fit for only a 2-parameter model. The right-hand side is the CO2 produced, which also is fit pretty well. And I won't say anything more about that other than to give you the data of it. To me, it is amazing how well you can fit data with only 2 parameters. And here are the summary of the 2 parameters. There's just a few things I'd like to call your attention to. First of all, these floods were all WAG floods. That means that water is alternating with CO2 during the course of the field. over here, this is the saturation in the unswept zone. This is the saturation in the swept zone. Here is change of saturation, which is one of the parameters. And here's the Koval factor. And I have to comment on a couple of them. First of all, the saturation in the swept zone is pretty darn high to me. It seems like it's a lot higher than anything you would see in a laboratory experiment, but that's what it comes out. And the Koval factor here is moderate to high too. Remember, one was a homogeneous reservoir, and these were fits to all of them. Now, there's more analysis to be done with this, and there's more things to be done with analyzing other field data. But I'm a great believer in this, and I will show this as we go forward. Here is the 50-year experiments, and this shows cumulative oil recovery versus total water injection in hydrocarbon pore volume. And the observations, well, first of all, these dotted lines represent the plus or minus 2 standard deviations about the mean right here. If you have good eyes, you can actually see the individual field response in here. But I'd rather call attention to the mean response and the variability. So here we are. There is substantial variability in performance. And so should we take this technology to CCS, we should expect substantial variability among the wells. In fact, we're probably going to have to drill 10 wells or more to be assured that there is enough capacity there to store a lot of CO2. The second is, there is, and this is not apparent on the slide here, but there is the quick response over here. And it turns out that the floods that respond the quickest also have the smallest ultimate recovery. And the logic is a little convoluted here, but one of the things here is that the CO2 is not just displacing oil, it's displacing water. So there's a combination of displacements here, and the maturity of the process is evident up to 4.5 pore volumes, and it would not surprise me if there were not floods now that are approaching 10 pore volumes of CO2 injection. Going on, the ultimate recovery is 5 to 15%, even though, and afterwards a substantial amount of oil remains. It's still target for recovery. Here is the things that are most of interest. The storage in the lower left-hand corner here is a schematic plot of cumulative CO2 This is injected, this is produced, and the difference between these two is the amount that's retained in the reservoir. And here in the upper left-hand plot is the CO2 produced. This is supposed to be a representation of this cartoon right here, and substantial, but not as much variability as in the oil recovery. And the plot over here shows the difference between the two, what this slide says retained. And as a mean behavior, the amount of CO2 retained in the reservoir is about 40% of the hydrocarbon pore volume, which is about the same thing as the CO2 saturation. One last thing to show is plot of total CO2 injection versus hydrocarbon retained over here. And once again, we see 40% retention, and the stored CO2 replaces the produced oil volume and the produced water volume. So it's not just knocking out the oil, which was the origin, I believe, of the practice of using hydrocarbon pore volumes for measuring the maturity of these processes. And because the residual saturation in the swept zone is so high, I have to claim that there's a good deal of mixing going on in the reservoir. And it's these sort of things, as Ian pointed out in the previous talk, that are understudied for research in laboratory settings. So, but the main lesson is that CO2 EOR can store CO2. Now, there is today even some doubt about whether you store it, and maybe when there's some doubt, you claim that because most of this oil produced is actually being burned, which is generating the CO2, maybe you're not storing CO2. But every calculation that I've made said that you are storing CO2 with these sort of performances. So here's some wrap-up conclusions. These are pretty much This is a plot of CO2 retained versus oil recovery. And then here are the implications. Injection wells should behave the same in CCS as CO2 EOR. That's because in most manifestations of CCS, there will be no production wells, and everything is all based upon injection wells. The Permian Basin, the total production rate is 300,000 barrels per day, or 30 megatons of storage per year. But the storage progressively decreases, especially late in the life of the reservoir. And as these floods become more mature, there will be less storage. Typically, half of the cumulative CO2 in the reservoir is produced. There's a great deal of technologies associated with separating the CO2 and a lot of research going on this sort of topic. And I can tell you what I know about it, not very much. EOR operators, and it's important to know, whose goals are not to store CO2, still achieve substantial rates of storage. And that is kind of the nub behind all of the storage efforts, is what in fact is the revenue stream, and the CO2 US is the revenue stream. And production wells are not anticipated in standard carbon capture and storage, but there's a school of thought that says we should perhaps dissolve the CO2 into water, inject the water, and then have production wells, because else injecting into a reservoir that has no offtake could lead to excessive pressure. And this is going to be one of the major issues going forward with CCUS, is the difference between injecting into reservoirs that have a sealed outer boundary versus reservoirs that have a transparent outer boundary. Now, I think that's my last slide. And so, Mauricio, I am happy to answer questions.
Thank you very much, Dr. Lake. Joseph, can you start reading out the questions, please?
Yes,
Yeah.
Thank you so much, Dr. Lake, for very good informative presentation. We have some questions, actually. What about this one? It says, how do you see the potential of methane emission and its utilization? Is it comparable with level of maturity of CO2 injection?
Well, every time you go to a different gas, there are some issues coming up with it, particularly with things like hydrogen. But there have been a fair number of methane floods, or so-called immiscible floods, and they perform pretty well. They perform kind of in the lower third of the CO2 performance. There's not nearly as many as, of course, and methane, of course, is a greenhouse gas, so it's a concern too. But it doesn't stay in the atmosphere as long. So I would say that yes, there is a future, and particularly for low pressure reservoirs.
Okay, we have another one. What's the effect of gas cap and aquifer on CO2 EOR performance?
Generally negative. That is part of the geologic characterization, is to know exactly where the gas caps and the aquifers are. And there's been at least one field case that was abandoned because the CO2 migrated into the aquifer. But this is kind of true of any EOR process, is that you don't want to lose the injection to an aquifer or to a gas cap. So yes, what that does is it restricts the target.
Okay, we have another one. Says, I have seen many cases where oil companies embark enthusiastically on CO2 EOR, but sadly they couldn't taste the success. Wonder if CO2 EOR depends on architecture of the reservoir along with reservoir and oil properties too. Please elaborate.
Well, that's a great question. And in fact, in one of my rehearsals for this talk, that a question came up again. We believe, and it almost certainly is true, that the success of CO2 EOR depends on the architecture in the reservoir, the heterogeneity, the seals, and things like that. But it's awfully hard to see that in that data set that I have, because it's all a big mix of things. And so operational strategies play a role in the things you just mentioned. So the answer is yes, but I can't prove it. Okay.
Okay, we have a question for Mauricio. Mauricio?
Yes, we have some questions. It says, many thanks, Dr. Lake, for interesting presentation. do you consider CO2 leakage in your graph, the CO2 retained figure?
No. Yeah, of course, I'm at the mercy of the data that's collected by the operators, and I don't think that they measure leakage, but I don't think there's a significant problem. I think Ian's talk previously actually touched on that, and it's not considered in the graph.
So Joseph, reminded everyone there is some question from Teams. Maybe you can choose one question from Teams.
Yes, we have this one.
Yeah, one question from Teams.
Okay.
Says, I really enjoyed Dr. Lex's presentation. Could he please comment on the potential of CO2 EOR for tight oil and shale reservoirs? One more question is related to 45Q tax credit. Can you comment on that?
Yeah, the 45Q tax credit, I'm not totally familiar with it, but it basically is a tax credit for producing, this is in the United States, for producing incremental oil. And it basically is not a subsidy per se, it's a reduction on your taxes. As I talk to some operators, they say, well, we're not really making any money, so we can't use that. But usually they find reasons to justify them using it because they claim they can make money in some other related enterprise. So it's a little too early to tell. Right now, the operators are just beginning to appreciate what they can do with that tax credit. Almost all of the ones that I have shown you are not taking advantage of that tax credit.
Okay, could you comment on the potential for CO2 for tight oil and shale reservoirs?
Oh yeah, well that's under test right now, and I'm cautiously optimistic by that. I have some references on that. Should anybody like to do it? The tight oil reservoir ultimate recoveries is really bad, and so there's a lot of oil that's being left behind. And the thing that everybody is afraid of is, of course, the tight oil is being able to inject it. But I will tell you, first of all, it's got the viscosity more or less of a gas, so that should help you inject it. And second of all, most operators have spent millions of dollars trying to increase the permeability of the reservoir. So I think it's not as bad as you would think from first blush. I do believe that you can do it. I do believe that it will be slow, and I do believe the ultimate recovery will be equal to or less than what you're seeing on these projects right here.
Thank you. We have one more that says, may I ask about the effect of the gas cap and aquifer on CO2 EOR performance? Yeah,
as nearly as I understand it, the question is the loss of the injectant. We simply don't, I don't think it affects the recovery in any chemical way or things like that. But there is, if you inject near a gas cap, there always is the chance that you'll lose that CO2 into the gas cap. And there is a chance that you will lose CO2 into an aquifer if you inject near it. And so you have to do great efforts to avoid it. Some operators use something called a water curtain, which, a bunch of water injection wells around the aquifer. Others have just basically lived with it. But of course, it debits the response if you do that. It's like throwing away a certain fraction of the CO2. So operators have, as a rule, avoided those areas.
Right. I think due to time, we really thank everyone's participation and Dr. Lex for his talk. I know it's very short time for questions, but as we mentioned it, we will keep an open space to answer all of those questions during the break and also through email.